So we are running actually on time, and it's time now to welcome the second keynote speaker of today morning. It is my pleasure to welcome Valentina to present Professor Strada keynote talk.
It's a great pleasure to introduce the next keynote speaker, Professor Mauro Strada, President and Technical Manager of STEAM SRL, an engineering and architecture firm with branches in Padua and Bari in Italy, and also in Belgrade, Serbia. Professor Strada graduated in mechanical engineering in Padua and worked as a full professor of environmental control techniques in Padua and then in Venice, teaching both to architects and engineers. About 10 years ago, he decided to completely dedicate his time to professional activities within his company. He has written more than 170 scientific papers on international journals, spanning from finite element analysis of natural convection to acoustic impact evaluation. Complexity is his bread, working mostly on the plant engineering design for larger and special buildings such as hospitals, labs, airports, museums, and theater in national and international projects. His deep knowledge of the physical phenomena underlying the design, operation, and management of any kind of built environment, combined with the practical sensitivity and pragmatism, allows him to use the right lens to identify and analyze the problem and to find the proper set of solutions. As a successful synthesis of different worlds, academic and professionals, his key point is the ability to interact profitably with all the different actors involved in the process, as we could experience from his keynote. The title of his speech is Recent Experiences in HVAC Designs and ZEP. Professor Strada, the floor is yours. Thank you.
Thank you, Valentina, for the presentation.
You lost the mouse?
I don't know.
We lost contact. Oh, here we are. Here we are.
Okay. Good morning to all. Well, we know that buildings are a sector that is really is very consuming energy. Is not only the construction of buildings, but the whole cycle of life of the buildings have necessity of a lot of energy to work. And HVAC, they are one of the major responsible on this energy consumption. What is happening is that we are making a lot of progresses on more efficient HVAC. But on the other hand, especially some kind of buildings like hospitals and so on, needs more and more ventilation, both for cleanliness of the internal environment, both for comfort and so on. So there are some strategies that we can recognize for trying to afford this increasing request for our plants, and to reduce the energy that they ask. The first one is well known, is the decarbonization, and so is using of solar energy by thermal panels or photovoltaic panels that can be coupled with heat pump or just used for giving electricity to chillers or so on. The second trend is the improvement of efficiency of production, energy production, by fossil fuels too. And there are many things you can see there. You can have three-generation, cogeneration too, that are well known. And after you can produce energy with different systems. You can use energy by heat pumps. You can produce chilled water only when you need it. You can use driving boat water for cooling a condenser in the summer, or for heating water for evaporator in the winter. Geothermal energy with probes that can be embedded, for example, in the poles of a foundation. Obviously, this system is efficient when you have a new building that you have to construct. And in this case, it's easier. But if it's just very expensive in any case. Thermal storage. Thermal storage can be by ice, by chilled water, and or from thermal changing phase systems. The problem is, again, the cost. And the second problem is space that they need, and not always you can find that space, especially in existing building. The third trend is improve the efficiency of our system. So it means that, for example, you can reduce the electricity that the fans ask in the air handling units by using inverter techniques, or you can use more efficient filters in your design. But I want to make a different way of explaining things. More than theoretical, I want to show you case studies of some kind of buildings that are buildings that need a very high needs of energy usually, where you can work for trying with many different topics. You can try to reduce energy. You can arrive to a near zero energy building, working on all you can find useful to reduce, to save energy that the buildings need. The first case is the laboratory. The example is the Biomedical Research Institute in Bellinzona. That's an Italian-Switzerland university institution, and they are building now, is now under construction, a new building for the Biomedicine Research Institute, the Oncological Research Institute, and the Neuropsychiatric Institute. All together, and there are both offices and service space, but many laboratories. Sorry. On the picture on the left, you can see that the building has a roof that is all covered by photovoltaic panels. No mechanical plants on the roof. And you have only 4 chimneys on the center of the roof. The center of the building are the exhaust air chimney, exhaust air that is obviously connected to the air handling units that are in the central core of the building. They are all in the central core. In this slide, you see the function diagram of the building, and again, it is written that in the roof no machinery, that air handling units are in the cores, but another thing that the technical stations are connected to the district heating of the city of Bellinzona, and the refrigeration units, the chillers, are cooled by groundwater, groundwater. One of the problems that we are obliged to afford is that in the center of the building there is a full 8 hole, 10 meters, is the entrance hall of the building, and has a roof that is a glass roof, and this glass roof is seal screen printed just to low solar factor. The east and west facing facades are motorized, are with motorized blister rail, and this obviously reduces again the solar radiation that enter in the hall. The hall has bridges on the 2 overfloor, the first and second floor, and there are bridges that connect the 2 parts of the building, but actually it's open. The air conditioning system has a kind of radiant panel on the floor, but with pipes that are embedded inside the slab, so we can activate all the mass of the slab, and in this way we have better results, like we can see later, better results for the comfort of people inside. Moreover, there is an air system with nozzles on the floors. Before all, we made a dynamic analysis using Transys software. I think you all knew very well Transys software. But this analysis was just to obtain the boundary condition for a computing fluid dynamics analysis. And this computing fluid dynamic analysis, made with finite element software, arrived to give results that say that we have a percentage of dissatisfied people inside everywhere less than 10%. So this was the last analysis, but we make many and many, changing the position of the air nozzles, changing the kind of beginning. We put a normal radiant panel on the floor, and after we saw that it would be better, especially in summer, to have activated mass 1. And there was continuously interaction between the skilled engineers for HVAC design and the engineers that work about this kind of simulation, that are something that in the border between research and application. But in the laboratory of this biomedical institute, there are problems that are over the saving of energy. And that means that in some laboratory, like the BSL-3 laboratory, BSL-3 is a classification for laboratory that can treat lethal pathogens, potentially lethal pathogens. You see some example like plague and so on. So they must be very, very accurate, analyzed, and many attention must be paid to this design. gap of pressure is absolutely important. Use of safety containers for the change of filters on the intake, and the systems, they need systems for materials. But we will see afterwards in a slide how we solved all these potential problems. In the Institute, there are also BSL-2 laboratories. And these treat pathogens that are not potentially lethal, but anyway are dangerous. And what's very important is protect operators from being invested from these pathogens. And that's a little more easy, if you want, because it is enough then the sacs of the wood, when the operator opens the sacs for example, half high, and in this case, the fume exhaust, the wood fume exhaust begins to work. The same, exactly the same airflow that we are exhausting by the wood, from the wood, must be reduced in the air handling unit, in the return of air handling units. So you maintain, that's very important, the velocity, the speed of air on the opening of the sacs, under the sacs, and that must be 0.5 meters per second in any time. We must not reduce to avoid that pathogens can enter or can go inside the laboratory and contaminate it. The BSL-3 laboratory are a little more difficult to treat. There are obviously standard, but you must every time think if you can make better. And so you have a full air conditioning, obviously, HEPA filter, that's obviously the same. And moreover, the filters must be placed in safety canister, because you can understand can be contaminated by the lethal pathogen, potentially lethal pathogens. The systems that can be subject to failure must be redundant, like fans, for example, and the control of the environment vacuum must be very, very accurate. You have always negative, obviously, negative pressure inside the BSL-3 laboratory. Like you see here, there are a pass box, all the materials that must send inside from outdoor to inside the laboratory must pass in this pass box to avoid contamination. All the materials that go out from the laboratory must be sterilized in an autoclave, and this is compulsory too. But what's interesting, you see in the filter is where the operator go inside or come out from the laboratory, but there is a bench, a passing bench, and the operator must sit down and change himself on the part towards the laboratory of the bench, and after can go out without leaving all the dresses, not the dresses, it doesn't go out naked, obviously, but the dresses that can be that are contaminated and can come out. Like you see, in this case, all our HVAC plants have a fundamental, really fundamental operationality for this kind of application. There are also the SPF, animal breeding enclosure. That means that there are the animals that for experiments, usually are mice, and they must be sterile, absolutely sterile, because in this case, we don't invalidate the experiment with something that afterwards the researcher injected in them. But you have in this case the two animal breeding enclosures that are maintained at positive pressure, and in this way are zones where must be no pathogen of any kind. You have HEPA filter that's normal, and moreover there is active charcoal filters for odor abatement. That's usual for the animal breeding enclosures. Let's pass to hospital. There will be a lot of things to say about hospital designs, of HVAC of hospital designs. But we can see that the most of the problems are very similar to that of laboratories. You must maintain cleanliness. And what happens is that now we have a really increase of requests of ventilation inside, especially the operating theater, the intensive care rooms, and so on. So it is very, very important to have, for example, heat recovery. But like the speaker that made the relation before me said that the heat exchanger can be pollution cause, and that there is the danger of cross-contamination. So it is compulsory to use some kind of heat exchangers for recovering of the heat or the heat from air from inside that go outside during the winter, or vice versa in the summer. This kind of heat recovery must be usually with two batteries, water batteries. You can't usually use in hospitals different kind of heat recovery systems. But in this case, you can obtain really high saving of energy. In hospital design, cross-contamination, all the other things, but I think that it's better to see something different. And there's another case study that is the new hospital of Treviso. Some numbers of these hospitals is 100,000 square meters of new buildings, 50,000 buildings that are undergoing restoration, 1,000 beds. It's a huge hospital at the end. And what is interesting in this case is that the design of this hospital, the detailed design of this hospital, was developed all in BIM, Building Information Modeling, that gives some opportunity to our work of HVAC designer to, you see, everything is in 3D, but this is easy. But what is interesting is you have models of mechanical plants, of electrical plants too, obviously, but for mechanical plants, and every component can be perfectly identified inside the design. And this gives, in the future of the life cycle of the building, an opportunity to make maintenance really in a better way than the usual maintenance in normal building. Why? Because if you have the map, a process map of everything and every component, you can, for example, make predictive maintenance. Predictive maintenance means that all the components work when they are at the best of their efficiency. When a component has a predicted number of hours of work, it can not only for failure, but can work with less efficiency, we go and we know that we must change the component. In this way, one of this thing is not so well understood somewhere. It is a way to make saving of energy, that every part of our plants work in the best way. During the construction of the building, you can avoid all the interferences between plants, for example, from electrical to mechanical, or from interference between plants and structure and so on. And in this case, you avoid, during the construction of the building, you avoid to remake things or stop and so on. And this is probably not saving of energy, but saving of energy of everyone that must work in the construction. Moreover, you can share with the other stakeholders. That means architects, structure designer, the building constructor, and so on, all the aspects of the building. This is the full model of that hospital. In this case, is architecture plus structures plus plants, every together. After, you can have only structures and plants, or you can look only onto the plants. And you have the whole vision, the whole view of the plants. And this is very, very interesting for when you want to make some change, because it is fast if you find that there is something that doesn't work, or you think that it's better to make something different for better saving energy or things like that. Well, it is very easy. You enter in a part and you change. Moreover, with the BIM modeling, you can make any kind of dynamic energy simulation. You have everything. You can look what happens in the life cycle of the building for 1 year, 2 years, 3 years, and so on. For example, for Treviso, with our dynamic energy simulation, we arrived to, with obviously the design we made before, to arrive to have a silver degree LEED credit, LEED certification. For the moment on the chart, because we must begin the construction. We began really a part, two buildings in restoration, but the large one is must begin. Another case study is the Bari Palese Airport. I think that many of you arrived there in Bari. Well, the terminal of this airport was analyzed from a point of view of saving energy. In this case, not only for the HVAC, not only for plants, but also increasing insulation of the envelope of the terminal. There are here some tricks. Tricks is too much. Some things that we made to improve the saving energy, the consumption of energy of the airport, but are quite easy, like use inverter for fluid pumps, and we improved the VAV terminals, and the BMS was implemented, and so on. And the building envelope was insulated not only with the construction of green wall systems for shielding the facades, but also with deciduous plants. Deciduous plants are very interesting. If you put the deciduous plants, they have leaves during the summer, so you have an effect of shielding from solar radiation in the summer, but they lose leaves during the winter, so you can have gain from solar, from sun. And this can be very, very helpful. You see here some of the view. There was a green roof too on the roof of the terminal. And afterwards, we used the existing skylights. In the terminal, there were many skylights, but we motorized them, and we interconnected them with the ventilation system. And when the condition of external air give the possibility, there is an enthalpy control, obviously, give the possibility to use the external air for ventilating, for having natural ventilation of the terminal. The system opened the skylights, and the air go inside the terminal. Like we saw in the first speech of a keynote yesterday morning, ventilation with natural air without consuming energy, but the one for fans, for the engine of the fans, is a very effective system for, say, air conditioning. Anyway, air conditioning of climate without spending money and energy for the chilled water for the batteries. We made another thing that is a life cycle assessment, because the doubt was, but okay, we use, you know, insulation, brise-soleil systems, we make new lights and things like that, but we spend energy, not only money, but energy for produce these systems. Moreover, at the end of the cycle of, for example, light and other things, you must dispose. So there is energy that is lost for disposal of this system. And with the life cycle assessment on 50 years, we saw that if you didn't do anything, we have what you see in the slide on the left, and with the improvement, you arrive at the results on the extreme right. So we are sure that it is not only a question of saving money or saving energy during the years of work of the system, but on a long term, we have results, good results for improvement of everything. Well, we are in Italy, so we have a lot of historical buildings. And these, well, are not strictly high-performance buildings, but actually they are, and we will see why. Historical buildings, most of historical buildings, can be used for new things. They can become museums, they can become university, they can become a lot of things. And so, at this point, we must put inside the historical buildings new HVAC. That means spaces that are not easy to find. That means, if possible, insulation of these buildings. And this often is not possible because they have a monumental value. And in Italy, there is soprintendenza alle belle arti. I say in Italian because it's very characteristic of our nation. That's right. They want to preserve this kind of buildings. Anyway, you must analyze very, very well what you can make inside this kind of building. But on the other hand, in museum, for example, sorry, in museums, you need our heating, ventilation, and air conditioning plants because you need to control the humidity and temperature variation on the artworks for conservation of artworks. And if there are some variation too fast or too high, you can have, in a long term, you can lost the artworks, some kind, not all, but some kind of artworks. So you need our plants. The other thing is that everywhere near the artworks, you must have velocity of the air lower than 0.15 meters a second to avoid that the dust goes on the artworks and things like that. Two case studies that are two museums. One is the Palazzo Fulcis in Belluno, in the north of Italy, in Veneto. And it is the new art gallery of Belluno. And there was another problem in this case, because Enel, that is the electricity supply, usually the electricity supply in Italy, in any case, if you want electricity power, you need to have Enel that gives you. Well, Enel didn't give any possibility to increase electricity supply in the art gallery, because for technical reason. We are in the center of Belluno, but real other technical reason. Well, so we were obliged to invent something for our heating and ventilation and air conditioning plants. And we used a gas engine heat pump. Heat pump, but work like chiller too. So we reduce in a very high level the electricity necessity of the building. Moreover, we used high precision air conditioning units inside any rooms. They look like fan coil, normal fan coil. They aren't. They have inside a humidifier, so they can control inside every room both temperature and humidity. And the BMS of the building obviously take under control all the rooms and gives orders to work or not the precision air units. These are some looks of the plants during the construction. In some rooms, it was possible to take out the floor and to use radiant panel. Not everywhere, obviously, because some kind of floor were not were so nice that it was not possible to take out. Well, this on the left is a Iaqvec stove. That was how the building was heated before. You can understand, very, very nice, but not so effective for a museum. On the right, there is a fireplace. It was the other way that was used for heating. Near the fireplace, you can see an old radiator. It's an iron cast radiator. Obviously, we took away. It was not possible to use again. And this is the result. On the room, we have the air conditioning precision units I told before. And on the right, in that room, there was the radiant panel, and the floor was a new floor, also if it looks like an old one, but it's actually a new floor with characteristics that the superintendenza obliged to use. That's possibly the nearer to the old one that was there. This is the final result. The art gallery now looks in this way, and it is currently working. We have all the results of the temperature and humidity inside the rooms. It is 2 years, and we are now analyzing them, but everything looks to go well. And at the end, we think that the work was effective. Another museum is San Domenico in Forlì. Forlì is in Emilia-Romagna, always in the north of Italy. And it is another restoration project. In this case, it was an old monastery that was transformed in a museum. The difference is that we didn't use the air precision units, but in this case, there was a full air system, the underfloor radiant panel, but a full air system with workable grids. This is during the construction work. You see that there are a large amount of radiant panel. This is how it looks now. The cloister. This is a night view of the museum. One of the rooms that are working. On the left, you can see the workable grill. The workable grills are very effective anyway, and they work very, very well. With the right speed, obviously. And everywhere there are sensors to be sure that on the pictures, I never get speed more than 0.15, like I said before. But everything is here too controlled by a very efficient BMS. On the right, like you can see, can have a view of the rooms of the museum. Thanks for the attention.
Thank you very much for this impressive example that are the real application of most of the research all the people is in this room is doing in his daily research, as we've seen in these days. I ask to the audience if there is a question, comments. Okay. Please introduce yourself. Thank you.
I'm Veronica Subarto from University of Adelaide in Australia. Just wonder, have you done post-occupancy evaluations from all the improvements? And if you do, if you could share some of the results, particularly on the satisfaction of the people who are using these buildings?
Okay. We make, just in the museums, because the other examples are things that are now in construction. No, for the Bari Palese too. In Bari Palese, in the airport, in terminal, you arrive there and probably you have the sensation that everything is working. But anyway, now we make some analysis, like I said before, by the BMS. The BMS is registering all the temperature and humidity value. we didn't ask to people, we didn't make, you know, a research on asking to people if everything is okay, if this is your question. For the museums, it's a little different. The problem is that in the museums, you must look before to the preservation of artworks. If you enter in a museum, at the end, you stay well. Usually there are no problem, but it's not the main target of the designer. The main target is I must make everything for the artworks, especially if I art gallery with pictures or things that are very, how to say, it's dangerous for their life. So they didn't ask to us to make a research about comfort of people. But we have no claim, so I hope that everything is working.
Other? Okay.
My name is Henk Kranenberg, and I have a question especially focusing more on the hospitals. And so also in the renovation of this hospital in Treviso, I think it was, with the air handling unit and the cooling system and heating systems, these are still centralized systems. Also learned in practice that centralized systems, they take a lot of space. Once they are installed, it's also a kind of limitation to the hospital to change the interior from rooms to other rooms, etc. Did you study a decentralized approach for air handling and heating and cooling services?
Okay, well, this is a very important topic in hospitals. It depends. Depends if it's a new hospital or if it's a restoration of an old one. It is different because it's a question of highness of the highness of the floor, or how to say, if you have enough space over your head, in the corridor especially. If in this case you can have centralized units and after run in the corridor, and you can how to say, you can use less air handling units. Why? It is better not to have too many, because there is maintenance problems. If you have many air handling units everywhere, the maintenance is more difficult, and you know that in an hospital, people that make maintenance must go in different different parts from the patient, the doctor, and so on. I try to explain. We must analyze in every hospital what we call the ways. I must have a ways for maintenance, a ways for doctors and patients, and a ways for visitors, for people that go for visit. And what means that if I have maintenance people everywhere, they are, it is difficult to make these ways in a way that is, how to say, affordable from a point of view of square meter. So, if possible, we try to have centralized air handling units. Moreover, filtering is easier for higher air handling units, and so on. In many situations, especially for renovation, you are obliged to have air handling units at every floor, and these air handling units, especially for, how to say, not so sensitive department. If you have, for example, operating theater, intensive care, or things like that, well, it is better to have large units with obviously redundancy, so 2 fans every unit and so on, or 2 different air handling units for the same, use, just to be sure. Moreover, there is another, in the hospital, you see, we need other 40 minutes by speaking about the hospital. In the hospital, there is another fact that any operating theater, it would be better to have air handling units, because if you must make recirculation inside, it must be only in that operating theater and with his air handling units. It is clear. So in this case, at the end, you have more handling units, smaller handling units. But for all other departments, well, usually you can have centralized one, as it's easier for maintenance, like you said before. I hope. If you want, we speak later on for about the hospital, how much you want.
Okay, I think that we can close this session. I don't know if Umberto has to say something. I just want to thank again Professor Strada for this keynote. So thank you again. So it's time for the coffee break.
Yeah, exactly. The coffee break has been served. I simply want to remind you that in 25 minutes we're going to start the Plenary session at 11 a.m. really sharp, because the day is pretty long. So don't pretend actually to stay eating food until 12, okay? Plus we have food available for lunch at 1 p.m. straight again. Thank you so much.